All right, moving on, I'll look at solving some logarithmic equations. So we look in these next two examples here, number 19, A and B. We're solving for x. Now notice where x is. Now an x in this problem, right, is in the logarithm, right? So we've got to get x out of there and solve for it. Well, to do that, we're going to use some properties of logs to help us simplify this equation. So right now on the left-hand side, we got two log base 10 logarithms. Remember our abbreviation for a common logarithm, a log base 10 logarithm, is just log. So I want you to remember the abbreviation there. So this is a common log. With that said, I want to be able to add these together. Let's go ahead and simplify the left-hand side. So we got the sum of logarithms. Well, if you remember, we can use the product rule. So I'm going to write the product rule up here. Product rule states log base A of m times n is equal to log base A of m plus log base A of n. So again, a sum of logs can be combined together by taking the log of the product of what you're taking log of. So here's my m and n in this example, right? X minus 8 and 5. So I want to add these together by taking the log of the product. So let's apply the product rule in my next step. So let's simplify this left-hand side of the equation. So this would be log base 10 of x minus 8 times 5. So there's the product rule, right? So I'll make a note here on the side that I just applied the product rule. And I added two logs together. So again, we're taking the log of that product. So now we've got log base 10 of x minus 8 times 5, after applying the product rule, equal to the log of x. Now let's go ahead and simplify what we're taking the product of. X minus 8 times 5, of course, what is x minus 8 times 5? Let's go ahead and distribute the 5 through. Right, that's 5 times x and 5 times 8. So that's 5x minus 40. So go ahead and write that in here as we simplify this left-hand side. Distributive property. So we distributed. Now, as we're looking at this equation now, we've got an equation in which we're trying to find x, right? That's our unknown. Well, x is in two logarithms. We've got two terms here, one on the left side, one on the right side, in which they're both log base 10 logarithms. Well, with that being the case, since we have a log base 10 on both sides, we know what we're taking log of, we can set equal. So if we know 5x minus 40 is going to equal x, right? So I'm applying my property, and I'll write that over here on the side, right? If log base A of x equal log base A of y, that implies x equal y, right? So again, we can use that property here and simplify that. So applying the basic property of logarithms. With that said, what resulted? Now we've got a nice, simple linear equation. So now we're ready to go find the value of x by isolating x here. So let's solve for x. So as we do that, we need to rearrange this term. So we'll go ahead and subtract the x over here and move it over to the left-hand side. And then we would go ahead and also move the 40 over. Go ahead and add it over to the right side. So we'll go ahead and add a 40 on both sides of the equation. So as we do that, all right, what do we have now in our equation? 5x minus x is 4x equal to 40. And our last step, let's divide out our coefficient. Divide out a 4 on both sides, and x is equal to 10. And now we just need to check our solution. And you do have to be careful with logarithms. Logarithms have the possibility of an extraneous solution. Remember, what you're taking a log of cannot be negative. But let's plug it in. So if x equals 10 is our solution, that implies log base 10 of x minus 8. Well, I'm going to plug in my answer. I'll put in a different color. that'll be 10 minus 8. So I'm plugging into the original equation, plus the log of 5. Again, that's log base 10 of 5, equal to log base 10 of x, so x is 10. So plugging in my answer, let's make sure it does check. Well, log of 10 minus 8, that's the log of 2, which is fine. So it should check and doesn't cause any problems with our domain. Doesn't have as a negative. We can't take log of a negative. And here we are with the product rule again. Right? What do we do with a sum of logs? We multiply them. So that's going to be log of 2 times 5. Well, log of 2 times 5 is the log of 10. So yeah, log of 10 equal log of 10. It checks. So yeah, we know we have our solution. So we've solved a logarithmic equation using a couple properties. Right? We used our product rule here in the first step to combine our sum of logs on the left-hand side. Right? Reviewing our properties of logarithms. All right, let's see what happens in our next example. So let's move on to example B. All right. So in this one, we're solving again for x. So again, what are we trying to take the log of? Well, there's my unknown. Well, then it's taking a log of in this problem. One thing you might want to note before we begin is x minus 5 would need to be greater than 0, along with x minus 7. So that means x is going to have to be greater than 5 and greater than 7 to be a solution. It'd have to be greater than 7. But we'll see. Let's go ahead and solve it, and we can check it in the end. With that said, this time I've got my log x terms. I have 2 of them, and I have a constant term, 3. Well, with that said, we need to group the x terms in this equation. So our first step is to go ahead and move this term over to the left side. All right, let's go ahead and add it over. So our first step is going to be to add a log base 2 of x minus 7 term over to the left-hand side of our equation. All right, so as we do that, all right, what do we get? We get log base 2 of x minus 5 plus log base 2 of x minus 7 equal to 3. All right? So we're just rearranging my equation. Now that I've grouped the x terms, remember I'm trying to solve x, we have another sum of logarithms. So we're applying that product rule again. So remember, quotient rule allows you to combine a difference, and you might run into an example where you're subtracting logarithms. And if that's the case, then you want to be applying a quotient rule. You want to divide what you take in the log of. But here we're going to be multiplying, because we're going to apply the product rule. So I'm going to make a note out here on the side. So as we apply the product rule, this is log base 2 of x minus 5 times x minus 7. All right, multiplying what we're taking log of. I'm going to put all that in brackets. So there's that product. So those 2 logarithms, right, have come 1 by applying the product rule. Let's get back to our problem here. Give me just a second. Sorry about that. Now here we are, back to our problem. So that's equal to 3. So we've got, again, our single log x term on the left-hand side, which is our goal, right? To solve for x, we're going to have to get the x terms together. So we apply the product rule. We multiply, we're taking the log of. Now let's go ahead and simplify that inside the bracket. Let's go ahead and do the actual product. What is x minus 5 times x minus 7? So let's go ahead and distribute that. So we know how to multiply binomials. X times x is x squared. X times negative 7 is negative 7x. Distributing the x through, and then I can distribute the negative 5 through. Negative 5 times x, negative 5x. Negative 5 times negative 7 is a positive 35. And now we've distributed, right? We've multiplied x minus 5 with x minus 7. And as we see here in this problem, of course, we have some like terms. So let's go ahead and combine those. So that'll be log base 2 of x squared minus 12x. Right? We have 2 x terms there to combine. right, plus 35 equal to 3. Well, at that point, right, I've simplified left side as far as I can go. Now, how am I going to solve this? Well, what we got to do next is what? Rewrite it. We got to apply our log definition. So here's what we got to know with the log definition. So keep in mind, what defines a log? Logs are exponents. So with that said, I got log base 2 of x squared minus 12x plus 35 equal 3. Well, let's write our definition back up here. We know that, and I can put it down here, we know that log base a of x equals some number y if and only if a to the y power equal x. So I want to go from here to there. I want to rewrite exponentially to solve it. So that's going to be my next step, is to convert this over to an exponential. All right, so let's go ahead and make that note. Rewrite it. Rewrite exponentially. So as we apply the log definition, we take log base a of x equal y. So my base is 2. That would be a, for example. X, what we're taking log of, which is quadratic expression. And y, what it equals, is 3. So if log base a of x equal y, that means log base 2 of x squared minus 12x plus 35 equal 3 is the same thing as saying 2 to the 3 power, there's a to the y, equal x, which is this quadratic expression, x squared minus 12x plus 35. So we've got a what? A quadratic equation. So the resulting equation is a quadratic equation. So after rewriting it, we get an equation that we can solve algebraically. We all know how to solve a quadratic, right? We would set it equal to 0 and solve for x. So let's go ahead and simplify. Of course, 2 cubed is 8. 8 equal x squared minus 12x plus 35. And then we want to set it equal to 0. Right, as we're solving quadratics, we set it equal to 0. We try to factor it, or we use the quadratic formula. So let's get it in standard form. Right. As we do that, we need to subtract the 8 over on the other side, right, to set it equal to 0. So we got 0 equal to x squared minus 12x plus 27. Well, if you wanted, you plug in your quadratic formula, right? You got standard form quadratic. A is 1, B is negative 12, C is 27. Plug in your quadratic formula and get your solutions. But hopefully, in a problem like this one, right, you see the factors. So I'm going to solve by factoring. I see the factors because we have nice integer factors in this example. I know that 27 has factors of 3 and 9, and 3 and 9 will work together to make that middle term coefficient, which is a negative 12. We know that negative 3 minus 12 is, or negative 3 minus 9 is negative 12. So let's go ahead and set those two factors up beneath it. So I need the x and x up front for the x squared term. And now I need my minus 3 and my minus 9. So if I were to distribute that, right, fold it out, I'm going to get x squared minus 12x plus 27. With that said, we're ready to apply the zero factor property. All right, so that implies what? X minus 3 can equal 0, or x minus 9 can equal 0. So I come up with two solutions to this equation. Well, I got to check these answers. Remember, we have the possibility of extraneous solution. So for example, let's check x equal 3. What happens if I were to plug 3 in? All right, here's my check step. So as we go back to the original, that would be log base 2 of x. And I'm going to take out x, and I'm going to plug in my 3. That'll be 3 minus 5, right, as we plug that in. Equal to 3 minus log base 2 of x minus 7. So that would be log base 2 of 3 minus 7. We plug in the 3 for x. And with that said, we have a problem. Log base 2 of 3 minus 5 is negative 2. You cannot take the log of a negative. Logs are undefined for those negative values. So we have to be values greater than 0. So that's our domain restrictions on logarithms. Can't be negative. That's undefined. Don't make that note. Can't be negative. That's an undefined value. With that said, that means x equal 3 is extraneous. So you see an extraneous solution come into play. Yes, a solution to the quadratic, but it's not a solution to the logarithm, which is what we're solving. Now, if you were to check x equal 9, let's check it. Well, x equal 9 as we plug in. That's log base 2 of 9 minus 5. Out goes x. In comes 9. Equal to 3 minus log base 2 of 9 minus 7. Again, plugging in 9. As we simplify that, that's log base 2 of 4 equal to 3 minus log base 2 of 2. And yeah, log base 2 of 4 is 2. It's 2 squared is 4. And then we got 3 minus log base 2 of 2. Well, log base 2 of 2 is 1. So yeah, 3 minus 1 is 2. So it does check. So even just plugging it in and simplifying, right, want to check our work, we can confirm that solution. So it does check. So we have one answer, x equal 9 for that one. So x equal 9 is our solution. So we had two answers. One worked, one didn't. You have to be careful with logarithms. So we do have the possibility of extraneous solutions like we did in that example. So I hope that helps. That's two examples of logarithmic equations where we had to use some properties, right, to help us solve. So we'll take a break and then we'll continue with solving some exponential equations. So we'll stop there for now.